Hello, ladies and gentlemen. This is going to be Chapter 9 quiz. This is problem number 18. Okay, let's take a look at the problem here. Salaries of chemists. I'll let you read this for yourself. You can pause the video to read it, and then I'll try to make a few comments about it. So pause the video, read it. Okay, now let's talk about it a little bit here. So what we have is we have a random sample from Washington State, and we have a random sample from New Mexico State. So what we have here are two samples that we're comparing. So that should be a big clue to you as to what kind of a technique we're going to use. Now, I've said this many times. Let me get down here to the end. At the very end of chapter 9, they've got a summary here, and there's two basic types of testing that we're going to be doing. Chapter 8 testing is comparing a sample to a population. So this is right here. You compare a sample to a specific population. So you say you feed Wheaties or you feed Raisin Bran to a bunch of kids, and you say, do these kids do better push-ups than the population at large? So that's comparing a mean to a population. So at the end of chapter 9, there's a summary here that I think is well worth your time to look at carefully. Make a copy of it. Always have it at your fingertips because it walks you through. It tells you exactly what to do. So chapter 8 technique is comparing a sample to a population. So that's this business here. Okay, now that's for a mean. Here we have a sample variance compared to a population variance. So that's still chapter 8, but it's a different test. Now we get to the third item here. This is a comparison of two sample means. So this is exactly what we have right now. This is going to be comparing two sample means. So look at this summary. It's very, very well done, and I think it's worth your time. Okay, give me a second here. All right, so we've got the two samples, and the question is there a significant difference between the two states in the chemist's salaries? So we're comparing the means, okay? It doesn't say the word means, but that's obviously what we're doing here because we're talking up here about average salaries. And then the second part of the question is find the 98% confidence level of the difference of the means. So basically, you're just treating the difference of the means as a random variable. So as you look at this, you know, what you should be doing is saying to yourself, okay, I know what this is all about. This is a chapter 9 type problem. I'm comparing the means, and my significance level is 2%. So they also want me to find the 98% confidence level. Okay, so we know how to do this. So let's take a look at the my notes here. Okay, as you know, I'm sure by now you've seen this many times. I have a standard technique, what I think kind of helps me stay organized. I hope you feel the same way. First thing I do is I write down what is it that I am given. I'm given certain information. So here's the information I'm given. Talking about Washington State. Okay, so I write down all the information. The N1, that's the number of data points. Okay, New Mexico State is N2. So arbitrarily, I've just said Washington State is set number 1. New Mexico State is set number 2. So I write down the information, and then I write down what is it that I'm supposed to find? What is the call of the question? Okay, the call of the question is there a significant difference between the salaries at a certain alpha level? In other words, alpha being, how willing are you to be wrong? What's your error budget is another way of saying that. And then it says find the 98% confidence interval. Okay, so here's a little discussion. I note to myself, and I recommend you have these discussions. It will help you a great deal, I'm telling you. We do not know the population variances. We know the sample variances, and we are comparing two means. Therefore, we use the t-test. Now, how do I know that? Well, maybe I have it memorized, but chances are I don't. So what I do is I look at the important formulas. I've already decided I'm in chapter 9. Here's the important formulas. It's on page 540 of your textbook of the 10th edition anyway. So here's my important formulas. So I go along here And I say to myself, okay, I know if I know sigma 1 and sigma 2, this is a formula I use. Well, I don't know those things, okay? So then I go down here, keep going here, keep going. Oh, wait a minute. Hang on one second here. Okay. Here's the other. All right, so this is a formula, the z-test, if I know the population variances. If I don't know the population variances, then I use the t-test. So here's the t-test. But in this scenario, I don't know the population, but I do know the samples, okay? And this is assuming that the variances are not equal. Now, on a previous a previous video, I talked about this scenario. What if the variances are equal? What do you do if the variances are equal? Well, it turns out there is a formula for that in the textbook, and I discussed that on a different video. In any event, we've got this formula now. So really, it's just a matter of plugging this in. That's all it is. It's the hard part on all of these is deciding which of these formulas do you use. What's the scenario that you're in? Okay. All right. So as I set up here, we're going to use the t-test. First thing we always do is we find the critical values. And we also we write down what the null hypothesis is and what the research hypothesis is. The research hypothesis, also known as the alternative hypothesis. So the null hypothesis is h sub 0, mu1 is equal to mu2. So what we're saying is that the average salaries for each state are equal. That's my null hypothesis. Remember, who has the burden of proof? You have to convince me, I'm very skeptical, you have to convince me that there's a difference between the average salaries. If you don't convince me, then I'm going to just assume that they're the same. Where it gets to be confusing, I think, sometimes is you look at the data points here that they gave you. In Washington State, the average is 39. New Mexico State, the average was $30,000. Okay, so 39,000 and 30,000. Okay, so you would be very tempted to just say, well, obviously there's a big difference. Look at that. Washington State is average of 39. New Mexico is an average of 30. Obviously, they're different. Well, you can't say that. That's not scientifically correct. And the reason why is because just by random chance, it could be that this sample that you drew right here, you looked at 12 different professors. Maybe just by random chance, you pick guys that had been there for a long time, or maybe the engineering guys get paid more than the English professors or something, and you picked all engineers. So there's all kinds of explanations. So what we have to do is we have to decide, is there a statistically significant difference between this average and this average, this X bar and this X bar? Or is it possible that the difference is merely due to chance? And so that's what we're always doing on these things, is we're trying to decide how surprised are we, and is it statistically significant or not? Okay. I know you've heard that speech before. Okay, so here's our null hypothesis. Here's our research hypothesis. The research hypothesis is that they are not equal. Okay, our significance level that we want is 0.02. We're going to use table F, and I'll show that to you in just a minute. That's in the back of the book. The degree of freedom is always going to be n1 take away 1, because that is smaller than n2 take away 1. In other words, we always use the smaller one. So n1 take away 1, n2 take away 1. So degree of freedom is 11. Okay, we're going to use table F, and we get a critical value of 2.718. So let's bounce back to the end of this this document, to table F. Okay, so here's the table F. This is the T distribution, as you can see. It says right there. The degree of freedom is 11. DF, that stands for degree of freedom. So 11. So this is the row we're going to use. And it's a two-tailed test. Here's the two-tailed test. And we want the alpha of 0.02. So this is the column we're going to use. Okay, so that's how we come up with the 2.718. It's merely a matter of looking at the tables and obviously knowing how to use them. Okay, so now we have determined what the critical value is. I'm sorry, I'm going to give you a headache here. Bear with me. Okay, so critical value is 2.718. Now it's plus or minus 2.718 because it's a two-tailed test. Okay, so that's how we determine what the critical value is. I urge you very strongly, draw these cartoons. It will help you understand what's going on. Okay, if our test value ends up in the shaded area, this is the critical value. I'm sorry, this is a critical value. These two numbers, plus or minus 2.718. The critical area is this area beyond the critical value. So if our test value ends up in the shaded area, we will reject the null hypothesis. And the reason we reject the null hypothesis is that if we end up either in here or in here, we're going to say it is so unlikely, it is only a 2% chance that we could end up in here or here, that we reject the null hypothesis. We say that there is a significant difference between the two X bars. Okay, so here's our test value. All right, boom, there it is. Where did that come from? Well, that comes from our formulas, which for your convenience I put right here. Okay, that's from chapter 9. That's the formulas that we're using. Here's the t value right there. So all I did, folks, is just follow my nose. I mean, you can be watching the Kardashians while you're doing this. It's not hard at all. Once you do a few of these, that's the key. You got to do a few of them. Okay. Okay, so there's the formula. Okay, what I do when I have something like this, it's too awkward to try to scribble out the answers or the calculations on the same page. So what I do is I do what I call a dictionary. I calculate the various terms individually. Well, how many terms have I got? I got one, I got this one here, I got this one here, I got this guy, I got this guy, then I take the square root of those guys. I mean, it really isn't as hard as it looks, okay? Just do them one at a time is my advice. So we're going to calculate them individually. Mu1 take away mu2 is 0. That's our hypothesis, okay? This guy right here is this guy. It's just a matter of plugging in the numbers. We come up with numbers, okay? I'll let you can pause the video if you need to look at this, okay? Then we add them up, take the square root, and there it is, okay? So now we have all of the various terms that we need. We plug everything in to what we started with. So my advice is do it the way I've just now shown you, separate paper, calculate them out and then plug them in. It may seem like it takes longer, but in the long run, you will save time. So you plug everything in, get your handy dandy calculator out, and there it is. T is equal to 9.807. That's a positive 9.8, blah, blah, blah. Okay, so what does that tell me? I'm well past the critical value. I'm looking at the cartoon again. The test value far exceeds the critical value, so we reject the null hypothesis. And what we say is there is enough evidence to support the claim that the salaries are statistically significantly different. Okay, great. So now the confidence interval. I'm running out of time, so I got to hurry through there. Here's the formula. It's right off of the formula page that I have at the end here. Okay, it's I don't know what to tell you really. We're treating this as a random variable. The difference of the means we're treating as a random variable. So it's this random variable plus the margin of error, this random variable take away the margin of error, and then in the middle we have the mu1 take away mu2. Okay, so the only thing it takes a little bit of effort is this guy right here. Okay, this is something we have to know how to calculate, but we already did that. We calculated that before. So we get a number here, okay? So the margin of error is going to be this times this, which gives me this, okay? Pause the video if you need to. So here's our interval. It's 9.205. Take away the margin of error, 9.209. I said 9 point. I should say 9,200. Give me 1 second. Okay, so I had a little technical difficulty there. I'm sorry. So this is our best guess as to what the parameter is. Our best guess, take away the margin of error, our best guess plus the margin of error. So that's how we come up with this interval that we are saying, hey, this is our best guess as what the interval is. And we have a margin of, we have this budget error, is error budget. Our alpha is 2%. We are going to be wrong some of the time, but we are only going to be wrong 2% of the time. So that's pretty darn good. Okay, so I recommend make a copy of all of this stuff, chapter 9 formulas, all the formulas. Make a copy. of that summary that I showed you a few moments ago. It will be well worth your time. All right, thank you very much.